my name is Aiden Arabzadeh, and this is the multi-bit register. The purpose of the project is to introduce the concept of flip-flops, memory registers, and the fundamentals needed to understand the SN74HC595 shift register. This circuit uses a data button and a clock button, which are used to input any combination of 8 bits on the LED bar graph. Here are all the parts I used on screen. At the center of the multi-bit register is the gated data latch, or D-latch, which acts as a 1-bit memory device because of its ability to latch 1 bit of data. The D-latch builds off a gated SR latch by removing the forbidden state of both inputs being high with a NOT gate connecting S and R to assure their inputs are always opposite. A lot of the times people mess up and commonly mistake flip-flops and latches for one another because of their similar appearances. However, there's one major difference. A latch is level triggered, so that means the output changes when the input changes, and a flip-flop is edge triggered, so that means it only changes state when the clock input moves from low to high or high to low. In this case, these are flip-flops because they have a clock input, and the output only changes when the clock input moves from low to high or high to low. In this circuit, a chain of 4 SN74HC74 ICs are used to create an 8-bit register. To input 8 bits of data serially, the first flip-flop takes the data on its input D and has its output pin Q connected to the D of the next flip-flop, and so on. Also, a PBNO with a pull-down resistor configuration is connected to the data input of the first D flip-flop, and one with a pull-up configuration is connected to a monostable 555 debouncing circuit leading to the clock inputs of each flip-flop. This ensures all serial transfers act in unison. As you can see here, all the clock inputs are connected to each flip-flop. When the clock button is pressed, the D flip-flop outputs a clock signal matching the state of the data pin. And when the data button is pressed, the data state goes high. Therefore, when the data and then the clock pin is pressed, a high is outputted on the first bit. However, if only the clock button is pressed, a low will replace the high state of the first flip-flop, and since Q of the first bit is connected to D of the second bit, Q of the second bit will match the state of its D input and go high. So let's write this out. So first, this data goes high, and this clock also goes high, and Q will be high. When the data button is not being pressed, and the clock button is being pressed, then it'll match the state, so it'll match the 0, but since this 1 carried on from the state before of the last flip-flop, this will output a high. This same pattern continues on. So whenever you press the clock signal, it will shift over 1. As you can see, I also attempted to make a 7-segment display, which took me a very long time. However, I forgot that with any values above 10 in binary, the segments will not display because they can only display from 0 to 9. Let's say I want to show an 8-bit binary value, with the most significant bit being on the right. For example, let's go with 100. That is 0, 1, 1, 0, 0, 1, 0, 0. Even though it doesn't read 100, that's because this is incorrect, but this is the binary value for 100. So let's go ahead and clear it, and let's go with another value. Let's say 225. That's 1, 1, 1, 0, 0, 0, 0, 1. And there we go. Thanks so much for listening, and I hope you learned something about the multi-bit memory register.